Hi everyone. So we are back with part two of our lecture on properties of functions. So in the second part, we'll do a couple of examples illustrating these properties and how to do proofs about them. So let's get into solving these examples. Okay, so as the first example, suppose we have a function f that maps integers into integers with the rule that f of m is equal to 3 times n plus 2, and function g that also maps integers into integers with rule g of z is equal to 9 times z minus 1. So the first question is, what is f circle g of 1? So that's f composed with g. So in English, we want to find f of g of 1. So first we have to compute g of 1. And we plug in the numbers, we get that it's equal to 8. And then we have to compute f of 8, which is equal to 26. So f of g of 1 is equal to 26. Now, how can we express f of g of x? Well, we have to plug in g of x into f. And here is the expression that does this. So g of x is 9 times x minus 1. And then we have to plug this into f. And when we multiply this out, we get 27 times x minus 1. So f of g of x is equal to 27 times x minus 1. We can also test it by plugging in 1. So if we plug in 1, we get 26, which matches what we got in the previous question. Okay, that's our first example. Let's do another one. If f of x is equal to 2x plus 1 and g of y is equal to y squared minus 1, then what is g of f of z? So g circle f of z is equal to g of f of z, and then is equal to, so first we have to apply f to z, so that's 2z plus 1, and then we plug this into g, so we get this squared minus 1, that is equal to 4z squared plus 4z plus 1 minus 1, and that is equal to 4z squared plus 4z. So g composed with f is equal to 4z squared plus 4z. And that solves this practice problem. Just as a quick sanity check, we can compute, for example, g composed with f of 2. That is equal to g of f of 2. So that is equal to g of 2 times 2 plus 1, that was f, that is equal to g of 5, and that is equal to, we plug in g, 5 squared minus 1, which is equal to 24. So that's one way to do it, and the other way is to plug it directly into 4z squared plus z. So g of f of 2 is equal to 4 times 2 to the power of 2 plus 4 times 2. That is equal to 16 plus 8, which is equal to 24. So this is of course not a proof that we correctly derived G composed with F, but it is a little sanity check that we did it correctly because these two numbers are the same. Okay, and that solves this practice problem. Let's look at the next one. So this one is related to relations. So given the set A, which is equal to 0, 1, 2, 3, 4, 5, 6, and the relation R defined on A times A such that R is equal to the set of pairs X, Y, where this pair belongs to R if X minus Y is divisible by 3. So now there we have a bunch of different questions about this relation. So what is the one set arrow diagram of R? So sometimes arrow diagrams are easier to do on one set as opposed to two sets, and this is one such case. And so this illustrates the mentioned arrow diagram. So 6, for example, maps to 0 because 6 minus 0 is divisible by 3. 6 also maps to 6 because 6 minus 6 is divisible by 3. Then 0 maps to 6 because 0 minus 6 is minus 6, which is also divisible by 3. So this is the arrow diagram that we get. And this arrow diagram is kind of interesting because this relation has a few interesting properties. So let's look at the follow-up questions. Is R a function? The answer to that is clearly no. Because, for example, 6 maps to both 0 and 3, which is not allowed in functions. The next question is, what is the inverse of R? So the inverse of R, we get it by simply reversing the arrows. Now, if you look at these arrows, you will notice that reversing them does not change the diagram. So the inverse of R is just equal to R. So what is the one set arrow diagram of R minus 1? It's just the same diagram that we have for R. What is the one set arrow diagram from R combined with R? So 4 maps to 1, then 1 maps back to 4 or to 1. So basically it's the same thing. So this arrow diagram is a diagram for R, R minus 1, and also R composed with R. So this wraps up this practice problem. Okay, let's see what else. So this is our last practice problem of this lecture. So we're going to consider a function f that maps Cartesian product of natural numbers into natural numbers, and the rule is that f of the pair AB is equal to 2 to the power of A times 3 to the power of B. Now the question is f onto 1-to-1 invertible or none of the above? So let's first look into onto. So if f is f onto, to show that f is not onto, we just have to find a counterexample. And it's really easy to find one. So most prime numbers will not have a mapping when it comes to f. So, for example, 7. So can f map to 7? So that would mean that 2 to the power of A times 3 to the power of B should be equal to 7. And that is not possible because 7 is divisible only by 1 and 7. So f is not onto. none of the pairs in its domain are going to map to 7, for example. So is f on 2? The answer is no. That also means that f is not invertible. Because to be invertible, it has to be both onto and one-to-one. Okay, now the final question is it one-to-one? Okay, so here we have to show that there are no elements in the codomain to which two or more elements from the domain map to. So let me think about this one. So I cannot find a counterexample, and so I will tentatively conclude that yes, it is one-to-one. However, we should do a proof that it is indeed one-to-one before we really can claim this for sure. So let's do this proof on the next slide. So let's do the proof that f is one-to-one. Okay, so let's remember the structure of the proof. So we start with an assumption. Let A1 B1 and A2 B2 element of n times n be given such that f of A1 B1 is equal to f of A2 B2. And then from there we want to prove that A1 B1 is equal to A2 B2. And so we have to use the rule and so on to fill in this gap. Okay, so if we plug in the rule for f, here we get that 2 to the power of A1 times 3 to the power of B1 is equal to 2 to the power of A2 times 3 to the power of B2. So because 2 and 3 are prime numbers, they're divisible only by 1 in themselves. And so from that, it follows that this equation holds only if A1 is equal to A2 and B1 is equal to B2. And from this, it follows that these two pairs are equal. And so this finishes the proof that f is one-to-one. Okay, so this concludes our lecture 12. So we'll continue next week. Thank you all for tuning in. Bye.